Okay, today we are going to basically continue what we have done yesterday, that is regular water waves part. First, let me begin writing some of the expressions that we have developed yesterday. What we had was in deep water, etc. So, this is what we had in deep water. What we have done was yesterday these expressions, and as I mentioned to you, if you look at these expressions, all parameters are essentially sinusoidal, both with respect to spatial parameter x and with respect to time parameter t. So, we will continue today on building upon this. First of all, I will introduce you the concept of group velocity and energy in waves. Keeping it aside, see, one thing that we realize, that this theory is based on linear theory. Now, linear theory implies, or the linearity implies that if I have, for example, a system like a black box, if I have an input I and output O, let us say input is I1, output O1, and an input is I2, output O2. If the system is linear, then I1 plus I2 would give me output of O1 plus O2, or conversely Ki would give you Ko. In other words, O and I are linearly related. What it means, if the box is linear, then I can have solution number 1 and 2 and 3, and I can add them all up and they still remain the solution of the system. Now, if I look at this linear water wave theory, I have a wave height eta 1, let us say A1 cos K1 x minus omega 1 t. Okay. And if I have another wave A2 eta 2 as A2 cos K2 x minus omega 2 t, what it means is that I can add these two up, and eta 1 plus eta 2 becomes the sum of these two, but the important point is that eta 1 plus eta 2 will also be a wave, possible wave which satisfy the same boundary value problem, which means that linear waves can be superimposed one other, and what we get is also a possible linear wave. So, they are very superimposable. That is the most important point, and you will find out that it has really a very high consequence as we go along the subject. So, therefore, the reason we can do that, a very simple example, let us say this one, it was a solution of phi 1. What was phi 1? It was satisfying the equation del phi equal to 0. This was a solution of phi 2, and I have the equation phi 2 is 0. But now, this equation is linear, because we know that del square phi 1 plus phi 2 is also 0 simply. So, therefore, like that we will find out that phi 1 plus phi 2 would also represent a feasible fluid motion, and since phi 1 solution is eta 1, of course, after the boundary condition phi 2 is eta 2, we end up getting that eta 1 plus eta 2 becomes a feasible solution. Now, this is very important, because what we will do now is that we will consider two waves and add them together and see that if the waves differ by a very small amount of frequency, then we end up getting a group wave. Now, before doing that, I will like to bring back to this eta expression, and I will tell you that it is quite often, when I have a sinusoidal function, easier to write as real part of a e power of I k x minus omega t as eta. Why? Because you or I can also write this as real part of a e power of I omega t minus k x. Both are same, because you see we understand that e power of I theta, okay, is equal to cos theta plus I sin theta, and if you make it minus, it becomes minus. The real part of both, that means e power of e plus minus I theta is nothing but cos theta. So, this is an expression that is sometimes used because it becomes easier to do operation algebraic operation very easily. So, we are going to use this expression because it will be easier. So, now we consider two waves. One is eta 1, which is written as real part of a 1 x, well, we can write it exponential as e 1 minus I k 1 x plus I omega t. Okay. Now, I am going to add another wave eta 2, which is real part of now, if you add these two up, we end up getting our, we do some manipulation a 1 I will tell you what is this. This is a simple algebra. If you did that, simply, you know what I have done is, you write k 2 as k 1 plus delta k, omega 2 as omega 1 plus delta omega, you simply add, you get. Now, the most interesting part of this here is that, see, any function which is something into e power of I k x minus omega t, real part of, this can be anything, is actually a waveform. It is a waveform travelling in plus direction with an amplitude given by this quantity. That is by definition, and by this is what it is. Now, okay, what is this part? Let us look at this slowly. This means, actually this expression means this into cos k x minus omega t, right. This expression, if I take a different pen, see, this expression implies something here, this star into cos k x minus omega t. Now, if I were to plot this, what is it? Is the sinusoidal form. This is nothing but a sine form of an amplitude given by this star. This star is this value. Okay. So, that means any expression with something into e power of I k x minus omega t is a waveform with that something as amplitude. Now, look at this expression. Here I have got something into e power of I k x omega t into this full thing, if you take the a 1 here. So, that means here I have got a waveform whose basically amplitude is this, right. So, I basically have a wave which having amplitude of this excuse me. Now, if you look at this part carefully, you will see that this itself is a waveform, because it itself has got e power of minus I dkx plus I d omega t. Basically, it itself is a waveform of length dk and period d omega and a speed d omega by dk. So, this means that the amplitude itself is an oscillatory curve and itself is moving. In other words, if I were to add the two together, that means if I were to add this wave and add the other one which is slightly different, see maybe here etc. If I were to add this, what I end up getting is actually a wave which will look something like which has an envelope. This envelope which is my A, this envelope which is my A star itself is moving with a wave velocity. So, the envelope itself moves with a speed. Okay. So, a lot of the students, lot of people have difficulty understanding how the two waves which is slightly differing can actually cause give rise to an envelope. Because you think that this is very nice sine curve, this is another sine curve. When I add the two sine curve which is only differing by a very small amount in length, how it can actually cause a modulation. So, the reason is like this, you know. Now, suppose you take this certain length, let us say, you know, it is easier to see in terms of length, say 10 units. So, every 10th unit 10, 20, 30, 40, 50 have a crest. Now, you take another one is 11 units. What will happen? 11, 22, 33 etc. In 55, this one has 55 a trough and that will have 55 a crest. You understand what I am saying? See, this is you see this way. This is very interesting to illustrate. See, if I were to do this 1, 2, 3, 4, 5. So, this 10, say 0, 10, 20, 30, 40, 50, 60, this is 55. But the other one will have this crest 11, 22, 33, 44 and at 55 it will have the top and here this is bottom. So, what happens if you add these two up, here the resulting wave will show actually 0. Somewhere here it will go up, that is exactly why this modulation will look like etc. You see, although it is differing slightly, but it will have. Now, remember this is evolving. So, this entire thing, this part would also appear like moving forward. This whole thing will move like look like moving forward. So, this is what is called group wave, and this particular you know, this envelope, and the speed of the envelope is known as group speed. So, we can also work this group speed out very nicely, because we see that this particular one is a wave of frequency d omega and speed dk. So, therefore, the speed of that envelope is going to be d omega by dk. That is by definition. Okay. Now, as long as d omega and dk are not perfectly 0, you have a group speed. Now, if you make a wave continuously, it is successive waves, you always have slight frequency difference. As a result, you always end up getting a group. Now, how do I get this? Now, you see in deep water I have omega square equal to gk. So, d omega by dk equal to, or rather I will say 2 omega d omega dk equal to g dk. No, sorry, let me write it again. 2 omega d omega equal to g dk. So, therefore, d omega by dk equal to g by 2 omega, half of g by omega, it is half of c, because g by omega was c, we have seen earlier. So, you see what happened. Therefore, what we end up getting is the group speed. If I were to call this group speed, the speed of that it becomes half the phase speed in deep water. Excuse me. In the other extreme, we can show that when kh tends to 0, that is very shallow, we can actually show that Cg tends to C, but that limit is of no interest to us. As I said, for this course sea keeping, we are mostly concerned with deep water cases, we are not concerned with shallow water cases. Okay. Now, this is very important, because what happens is that now the energy of a wave always moves with that speed. Let me now come to, now before going to the energy propagation, let us now establish energy relation itself. Okay. So, group speed we understand. Now, let us look at this energy. Obviously, the energy expression, if you do kinetic energy and potential energy, will look to be integration over volume of, see, it is velocity square and position. So, it is okay. Now, so this is the total energy. Actually, if I were to do this, if we take a vertical column of water, that is, I take a vertical column of certain area, look at the energy of the waves, what would happen is that this expression will turn out to be minus h by eta. In fact, we need not do all this thing. Now, if you work this out, okay, we are not going to the detailed working, but if you work it out, it will turn out to be, this expression will turn out to be omega now. This is how it happens if you do the manipulation. Now, this is this part k eta, what happened? Remember, we have said k eta is small, it is small amplitude wave theory, eta is height, k is inverse of lambda, that is k eta is proportional to eta by lambda, right. So, is now e power of some small quantity, that to twice e square, you know, if I call k eta to be an epsilon, it is e power of 2 epsilon. So, this part becomes very small. So, linear theory, it is consistent to neglect that, because this is actually second order term, because k eta is of order epsilon, 2 k eta is order of 2 epsilon. So, we end up getting this relation. Now, this one, if I were to put you all the expression for eta, you know, like eta etc., we end up getting E, again I am just writing with a derivation as 1/4 rho g a square plus 1/4 rho g a square cos square kx minus omega t. In fact, this is my potential energy, this is my kinetic energy. And now what happened? Obviously, kinetic energy is, you know, showing this sinusoidal dependence term, because particles are not constant, they are continuously undergoing changes. Now what has happened? If I were to integrate energy over one period, you know, like if I take a bar here, I kind of measure the energy from 0 to time t, total energy in that, and divide by t, then what I will get is what is called average energy over an average surface area, 1 unit surface area, average energy. If you do that, you end up getting E bar to be equal to half rho g a square. Actually, what you end up getting is that this become half rho g a square, 1/4 rho g a square, this is 1/4 rho g a square, so the total is half rho g a square. So, this is my average energy. Remember, this average energy, instantaneous energy is different because of this time dependence. So, average energy over one period 0 to t over a unit area on the surface is this. In fact, if you see the unit, you will find the unit of that is energy per unit area, the unit of that. Okay. Now, having said that, it turns out that if I were to, this also we fix an attention of to a vertical fixed observation line, let us say some constant line, we will find out that energy flask travels through that line, that is dE by dt, turns out to be Cg into E bar. Again, this we are stating without proving that. There are number of ways to establish that. What it means is most interesting. The energy travels forward with group speed, not with phase speed. Okay. So, phase speed has nothing much to do with the energy, the physical quantity. Phase speed is to do only with the form. This is something that we must understand, whereas group speed is to do the physical quantity like energy. Particles, for example, do not move at all, they are like a circle, okay. But energy does move forward. Obviously, it makes sense, because if I have a calm water here and if I were to turn on some wave making device, you will find out that water is basically moving forward and energy will be propagating at group speed. So, this part is very interestingly seen this way, like supposing I tune a wave maker at some point at this time, you will find out that at some time the wave is like that, next instance wave is like that. So, this front would have moved at a speed, this is actually say t with time. So, like this is at some time the location of the front, next instant, etc. But if I were to concentrate on any of the phase, the form, you will find that these actually move at twice the speed. Then the confusion come in people's mind is that what happens to this? Actually, what would happen is that as it catches up here, the amplitude becomes 0 and there is no phase speed basically. In fact, you simply disappear, like this line do not exit any further. How it happens? Why? Now, there is a physical explanation. How do I explain this is the speed of energy? No, it is very simple. You see, initially this is calm water, if I take a line. So, at this point I have no energy at all, it is calm water, but just next point I have energy because wave is existing here. Now, so naturally next instant this front has moved here. Obviously, the energy has moved up to this point because just here there is no energy. So, this front obviously carries energy. So, this is exactly why the wave front is moving with energy, and same thing will happen to back. If you switch it off, this back line will also go like that. So, this is actually so classical. I keep telling that it is in fact on the cover page of that J. N. Newman's book, the flap, this very nice actual picture taken from an experimental wave basin and photographs. So, this is extremely important that we have this. Now, this is we will find out afterwards, because we may have a question, why are we studying this energy, etc. Where do they relate to my ship motion? We will find out that yes, there are very good application of this eventually when we talk to ship motion. For example, even earlier we have seen in wave resistance, for example, the energy propagation is extremely important, because if the energy was propagating at the same speed as the ship, then you end up getting a very large resistance, energy getting trapped, just like in sonic boom case of aircraft. Similar thing would occur in ship motion also, in spectrum when we will go to that. So, energy relations become very important. Okay. Now, having said the energy part, now I want to go to the one more aspect which becomes very important when we study wave effects on floating bodies, structures, ships, etc. That is connected to the concept of, let me take this off, phase. You see here, when I write an equation eta equal to A cos kx minus omega t, well, I can write this kx minus omega t here rather, and the graph looks like this. But now, if I were to add an angle here phi, what it means is that it means that I actually shift. You see what happened, or rather maybe another one I will tell. Better way of doing is eta equal to, let me just write this way, A cos kx, just A cos kx let me call initially, and I add what phi. What would happen, that you see here earlier when my phi was 0, at x0 my eta was A. Okay, that is when phi is 0, this is my x here, is my A here. But when my phi is having some value, then what would happen is that when x is kx equal to minus of that value, that is it is somewhere else, my this should shift. What it means is, in fact, I am actually relocating the x axis, because I can always write this as x, I can take k out and I can say x plus phi by k, etc., etc. Basically I am changing x to x plus phi by k, which means I am changing this origin, which means that now my graph would probably look like, in this case, when x equal to minus phi by k, then it is 0, because this must be 0. So, somewhere here, so it gets shifted. Either way, this it depends on which side you take, you know. In fact, I can say that sine curve and cos curves are nothing but phase shifted curve by 90 degree. Okay, so this shifting of phase is very important. Why? Because what it means is that phase tells me the location of its peak with respect to the x coordinate, which could be, of course, in this case physical x or time t, depending on what you are looking at, or kx minus omega t. So, when I am writing this expression of eta, earlier what we wrote, that we said eta equal to real part of a e power of minus I kx plus I omega t, whichever way you can write, it is okay. Now, if I were to add a beta here, which is nothing but saying e power of into e of I beta, actually this there will be I here, because the entire thing is under I. Okay. This is my phase, and this tells me with respect to x equal to 0 where the and t equal to 0 where the peak occurs. Now, this is very important, because what happened in water wave mechanics and in the floating body response subsequently, things do not occur at the same time, the peak value all. So, if something happens highest now, something may be lagging behind it. See, I want to give you this example. Maybe if you look at this, my hand, supposing I twist my hand, I said that before probably, you will see that if I were to see my hand, this tip point, it goes this way, but this point may not exactly follow that. That means, if this is having a peak here, if you observe, you will find out that my this one is actually reaching. See, I go here, as I come back, it is still going up. You know, if you do this way, as at the instant you begin to come back, it is still trying to go up. So, that means this tip's oscillation is not phase synchronized with my top oscillation. So, that would occur something like, see, it is occurring here, that would occur slightly later, that will actually go like that. So, this blue one would be my this point, and red one will be my this point, the oscillation. This is phase. This is what exactly what we are talking of, phase shift, you know, and this is extremely important for us from all points of view, because later on we will find out that things do not occur simultaneously. When a body is, for example, the wave is moving up, the body may not move up, although it is still sinusoidal. So, phase is extremely important, and we need to realize that. Now, what does it means? Now, let me look back at this first expression of, that is why I wrote this first page of all this expression here. I will come back to this in a minute. See here, what happened, you know, you see here eta is a cos curve, but W is a sine curve. Okay. Now, if I were to plot eta and W now, okay, what would eta look like? Eta will look like, let me take another one. See, eta will look like this, a cos curve, there is eta, but my W is a sine curve. So, the W will look like, it is a positive sine curve, so it is going to look like this, sorry, like that. So, basically you can say there is a phase gap, and that is very easily explained, because a cos curve is nothing but, well, sine is nothing but cos plus minus 90 degree, plus 90 degree, yes, plus 90 degree, right. So, what happened is that essentially sine and cos differ by a phase of 90 degree, and I can always say therefore that the phase between eta and omega W, sorry, is 90 degree. Now similarly you will find out there are all kind of phase, which means the topmost point I have actually not the highest vertical velocity, which also makes sense because the particles are moving this way. At this point my velocity is most this side and downward velocity is 0. Whereas at this point somewhere here my downward is maximum, x velocity is 0. So that is what is the phase, and that is extremely important. Now the one problem that comes is, in how do I measure phase? It is like I have a graph, number of graphs, see this one, see another one here. Essentially the phase tells me gap between various graphs, time gap, but I have to put them in number in some sense. So what happens? I have to measure phase with respect to sum. So what normally people do is that you write eta to be real part of E I k x minus omega t, or whichever way out, right, and measure everything with respect to this as phase, which means mostly phases are measured with respect to eta, taking eta to be a cos curves with respect to it at x equal to 0, t equal to 0. That means if I were to take an origin here and I consider eta to be like that, that is occurring maximum here, with respect to this signal I am measuring the phases. You can always debate why this way, I can also measure another way, no problem, because phase after all the information content is what is the gap between the two, that is the information content, as long as you can get it. Now you know that supposing I say that like I let me give another example. I say that eta equal to a cos kx minus omega t plus 45 degree, and then some other signal say r is a cos kx minus omega t plus say 89 degree. What would happen is that you can always say with respect to some reference eta is having a phase 45, r is having a phase 89. But I can also make this 45 as 0 and make this actually as 44 degree, right. That makes more sense generally in our study, because we will find out in C keeping study what we are trying to do is that measuring everything with respect to eta, because eta is my primary input. Remember what we are want to do. What we want to do is, I have a wave, my ultimate aim is what does the wave do to my ship, how does my ship move, how does my body move. So eta or the wave is my primary input. So I want to basically measure everything with this eta, but it is not mandatory, it is up to you, as long as you do not make a mistake. What my point is essentially this. So given another example, that the phase relations are very well established with respect to, for example, various signals. See, if wave profile eta goes like this, it turns out u will having the same phase, this is my eta, this is my u, then my w goes like that, then my w goes z component, the acceleration, x component of acceleration will go like this, that is u dot, and this will go like that, w dot. So you know what I am trying to say, that this is all the as far as the acceleration velocities are concerned, the relation is very well established. This of course everybody knows very well that in a sinusoidal signal the displacement, that is theta or phi, the velocity, that is grad phi, or you can say phi dot if I want to tell, and the next integration all differ by 90 degree. That is why displacement and velocity 90 degree, velocity acceleration 90 degree, displacement acceleration opposite. That everybody knows it in any signal, but it is also very easy to see, because if you write anything as like x equal to a cos something, say omega t, then x dot is going to be minus omega a sin omega t, x double dot is going to be minus omega square a. So you can see this and this opposite 180 degree, this and this 90 degree, etc. So this is very well established, but what will happen to our subject subsequently is that I have this wave here. Now I know everything of that, but I have going to have a body here, this body's motion or response or force or pressure whatever, I have to figure it out. It will also be sinusoidal, which I will come later on, but it will not occur exactly in the same phase. It will occur sometime later, sometime before. The phase is very important, and also it has a very practical meaning, because for example, take pressure. If all the pressures were going to occur at the same phase, then I would have a very large load when there is a like a crest coming, and just the opposite when trough coming. It does not happen that way. So, this is very important that we understand about the phase relation. Okay. Having said that, now let us try to work out some simple problems, rest of the time. Let me try to. So, we will now spend the last few minutes of this class on trying to do some kind of a problem with also involve maybe phase. Now, suppose there is a tank. The problem says there is a towing tank, (150 m) long, 5 m wide. There is a wave maker in one end, and this is what we. This pen is not so sharp. Here is another one. Let us say the problem says that let us make, we are making a regular and t equal to, well, the very simple problem, find out omega, which of course absolutely simple, we do by this 2 pi by t. Okay, so this will turn out to be 2 by 2 into pi equal to 3.14 radian per second. This is very elementary, just to know about how to get omega, k, etc. We will come to the phase problem in a second. K of course is 2 pi by lambda. Now, how do I do this 2 pi by lambda? Now, you tell me this. So, we have to use the dispersion relation first. So, dispersion relation tells me I have to get actually this thing, but we can also, without that we can do C omega square equal to g k. So, k is simply omega square g, this, right. This also can be omega square by g. We can straightforward use that, which is the same thing, you are just using the same thing differently. So, this will turn out to be something like omega square is in this case pi square by, we approximately come to be about 1, okay, 1 meter power of 1, and lambda therefore come to be approximately 6.25 meter, 2 pi, basically 2 pi, right, length. Now, it says that find out maximum fluid particle velocity in the tank. Let us say tell me this. Now, you see here we will have to go back to our expression for what we have done before of u and v. Now, you see here what is the maximum u max? This is this, right, because it is, remember that maximum value of E k z is only 1, because z cannot be positive, z is 0 to negative. So, this amplitude is maximum value, similarly this is maximum value. So, you but then remember that the total maximum is not going to be simply sum, because the maximum now there is another point, u square plus omega square you cannot do by these two addition, because when this happens this is 0, remember when this happens this is 0. So, the maximum would occur actually this only, the modulus. Do not use u square plus omega square with this value and the square root it. So, we end up getting this maximum particle velocity to be something like if you work it out about 0.63 meter. Now, what is celerity? C. C is going to be omega by k. How much it comes to be? It comes to 3.12 meter per second. Okay. And now the question is, the interesting question on a phase is there. Okay, that this question says like this. No, it is phase speed, not group speed. We are talking of phase speed. See, phase speed means this form speed. Group speed is the front speed, which I will come. The next problem is on the group speed, but here this particular question is now on the phase. What is the phase? This you see now. So observer is standing here. Okay. The question is, what is the phase of the wave? 2.5 meter here. Okay. So you see now this is how do you work it out? Now you see this is the observer standing here, and what the question is, what would be the phase if I were to go 2.5 meter towards the wave maker side? This is my wave maker. So now see, with respect to this, if I were to call this to be x, okay, what is my eta? See, suppose this is my x, I start from here, then it becomes eta equal to a cos kx minus omega t. But now the question is that I need to call this measure with respect to this, or rather I have to find out this with respect to x equal to here, right. So now this is 2.5 meter. So what is happening, that I have to measure this with respect to a parameter when x has been met, see, by this x plus 2.5 meter, right, because see, if I were to measure something, any point here is x, but if I measure from here it is x plus 2.5. So the expression for that with respect to this point is going to be a cos k x plus 2.5 minus omega t. So this, if you work it out, it becomes k x minus omega t plus k into 2.5. Now k into 2.5 is therefore the phase. What is k into 2.5? 2.5 into 2 pi by lambda, what we found out earlier is k is 1, yeah, absolutely. So it is 2.5 radian, straightforward. So it is like this, you end up getting therefore that 2.5 radian, which will be about 144 degree. This is the idea for the phase. Okay. Now we will see one more case where the question was asked regarding this group speed that we will work out. Now here it says another, again a wave maker problem. Okay. It is making wave of frequency omega, period, well actually in fact omega or period is given as 2 seconds and amplitude A is given as 0.25 meter. Tank length of the tank is. Now here the first question, approximately how long will it take for a wave front to propagate from the wave maker to the other end of the tank? Okay. First question is, how much time will it take the front to reach the other end of the tank? Now the question here, what the question was asked, this time taken for wave front this is going to be L by Cg, right, because the front will travel. So, what is Cg here we can first find out. Now, in this particular problem assume deep water. So, my T is given. Okay. Now, how much is C? First of all, you have to find out your C. C is we can always C is omega by k, and let's see how we can let's write in terms of like T. See omega square being gk, C omega by k equal to g by omega equal to g by 2 pi lambda, right. So, C is this thing g into lambda by 2 pi. Now, of course, lambda we have to again work out, let us say no, actually no, sorry g by omega we can write simply g by not lambda T, this is T, making a mistake. So, this is like this gt by 2 pi, how much this comes, T is 2 second. So, it is g by 2 pi into 2. So, g by pi, that is approximately let us say 3.2 meter per second. So, therefore, Cg is 1.6 meter per second. So, therefore, time taken is going to be 100 by 1.6 second, approximately is equal to 100 by 1.6 would be about how much, 62.5 second. So, this is the group speed. Okay. Now, I am going to do one part which I will now leave it for you to work out, because it is with respect to this thing phase again. Now, see here I will write it down. Consider an observer situated along the tank side time okay. This next part, of course, this is of course very simple, this part, because the answer is that it will be the phase speed, like after the wave front has passed, you are standing and you are trying to now see the crest passing. Now, you see what will happen is that the crest will pass much faster. So, you will actually see it far, but the important point is next one. What is the this also we have done last time. See here, this is what we have done before. What is the phase of the wave elevation? 1.5 meter closer to the wave maker relative to the wave elevation at the position of the observer. Important point is this, see, this phase is being measured relative to the wave elevation. You have to measure phase always with relative to something. You just cannot say phase is so and so, it makes no sense. The word phase necessarily connected to a measurement. But now there is a second question, is that what is this phase, this part, what if the observer is traveling, moving with a velocity 1 meter per second, either towards the wave maker or the other way around to the wave maker. I will explain this picture in a minute. This I will leave it to you for thought. See what happened here now, this is a tank here, okay. Wave maker is here and waves are going past it. Now you are standing here, let us say standing here. Initially of course you are saying that with respect to that what is the phase, simple problem we have done last time, but now the question is more interesting. Now I want to define the wave with respect to a moving frame of reference. See earlier what happened, if I want to find it out, all I have to do is to measure this as my reference frame. If I have my cos kx minus omega t, I simply define x with respect to that. But now my x is variable, because what is happening is that I am actually walking towards this or walking towards this. Now remember this, supposing I was with a crest, see the physics is, and I was travelling with a phase speed. What will the phase gap? 0, because I will always see my crest in front of me. If I was going slower, my crest will have passed by. If I other way around means something. So what would happen? There will be a phase gap, but the phase gap is not going to be constant, because what would happen in this case, phase gap would keep on evolving with time. That means my phi, that is kx minus omega t plus phi, would become a function of time t. So therefore what happens is that in this problem you end up finding out an evolving phase, because it is not going to be constant, and that is what maybe you could work out for the next class, and we would kind of see this. So I am going to more or less end it here today on the wave part. This gives us a kind of a basic understanding of linear water wave that we are going to use continuously when we study sea keeping. I will close it by saying that water waves are sometime a little bit difficult to understand, because by wave we always mean the form, where the particle never follow the form, particles have a different motion. So the dynamics involved is not as severe as it might think, but it may also be more. What I am trying to say is that what you think intuitively may not always work. It just does not work, because the very fact that two waves can interact is an interesting example. I can look at a calm water and I can tell you theoretically it is equal to two waves of exactly opposite phase. It is like saying 4 is equal to 2 plus 2 minus 4, or equal to plus 4 minus 4, equal to, or 0 equal, rather other way around, 0 is equal to 2 minus 2, or minus 2 plus 2, or whatever. So the waves are like that. So there is some kind of conceptual understanding required. What we talked of only one wave, when we add the fun will start, because when we add we will find out that I can always say calm water, as I say, sum of n number of waves. And now we will find out in a wave maker. I will just end it by saying, supposing I say that, and I say that suppose you have a wave maker and you want to make a wave by pushing this way, and we find out that if I actually have two waves of out of phase, I have no wave at all. Okay, now the question is, how do I make it to move? Can I at all make a like wave maker move so that there is a calm water? The interesting part is that if supposing person 1 wants to make a wave of phase A, so he wants to push it, and if person B wants to make a wave of phase minus A at that instant, he has to pull it. So both will pull and push, and the plate will remain steady, and therefore it is like force is plus 1 minus 1 is 0, water also remains 0. So it gets explained by that. So you cannot move a plate to make a 0 wave, because the movement is going to be 0. It's like doing nothing. So this is what, but then we will always tell that yes, calm water is 1 minus 1. With that I am going to end it, and we will go tomorrow next class onwards to the actually now we will begin to put the ship in waves, in regular waves. Thank you.